Recording. Okay, I think in the last session we covered up to like linear transformations. I will cover those things if needed, right? So I think there are one or two Tamil guys out there, so I will explain in English also. So if necessary, I will explain in single. So first, we have to learn about this. First thing is you have to learn about eigenvalues, right? So we have to start with eigenvalues and eigenvectors. So before going into the definition of that, as usual, I will explain what are those eigenvalues are. So why we need eigenvalues and eigenvectors. So what are they actually mean? So because not knowing that, you cannot do any of the diagonalization or any other operations without knowing properly what eigenvalues exactly are. Let's say you have some matrix, say something like 1, 3, and 7. Let's say 2, 4, 5, and you can have 9, 8, 1 or something. Anything you can have, right? So then you can have anything like that. Then you will have some sort of vector. Let's say you have some sort of vector 1, 2, let's say 1 or something. So then you have a matrix and you have some vector. So let's say this is X. So you can think of this as matrix product AX. If you multiply this, you will get an answer. If you properly do the calculations, you will get 1, 3, 7. It means 1 plus 6 plus 7 means 13. You will get, and then you will get 2, 4, 5 means 2, 8. It means 10, and 5 means 15, and then 9, 16 means 25. 25 plus 1 is 26. It means you get another vector. So key thing to here notice is you get some vector and multiply with by this matrix A, and you get another vector. So when you compare two vectors, let's say when we let's draw this geometrically, you get some vector like this is origin, and you draw some vector. Let's say this is your vector X, and after multiplication you will get some other position vector, something like this. Let's say this is V or AX. In other words, basically you can think of it as like a position vector with respect to the origin, any vector in any dimensional space, 2-dimensional or 3-dimensional. So then what would happen if you compare these two vectors? Two things can change between two vectors, because vector has two things. One thing is you have magnitude, and the other thing is you have direction. Okay, so you have these two things in a vector. So then what would happen? So if you multiply by this vector with a matrix, what would happen? Either of these two can be changed. So it means it is necessary, because if you, let's say if this multiplication is something like this, you input some, give some vector, and you get another vector. So if you compare this vector and this vector, you can compare their magnitudes and their directions. The eigenvectors is a special kind of vectors. It is something like this. It means AX equals lambda X. This is lambda is a scalar. It means if you give you an eigenvector to this multiplication, vector multiplication to this matrix, what would happen is it doesn't change its direction. It doesn't change the direction of the vector X. Instead, it just change only the magnitude by the lambda amount. This thing we call eigenvalue. I will come back to it later. The key thing is this is some vector transformation, because you give some vector and get another vector. So when you compare the both input and output, you can compare its magnitudes and directions. Basically, that is the main thing that you need to understand, because if you multiply vector, you one vector and get another vector. And සිංහලෙන් කියනවනම් අපි වින්‍යාසකකින් මොකක් හරි AX කියන ප්‍රොඩක්ට් එකක් ගත්තට පස්සේ X කියන වෙක්ටර් එක A වලින් වැඩි කරාට පස්සේ අපිට හම්බෙන්නේ V කියලා වෙක්ටර් එකක්. ඒතර මේ වෙක්ටර්ස් දෙක අපි කම්පෙයාර් කරන එක. අපි ඉන්පුට් එක දීපු වෙක්ටර් එක, අපේ ඔරිජිනල් වෙක්ටර් එක සහ අපේ මල්ටිප්ලිකේෂන් එකෙන් පස්සේ ආපු වෙක්ටර් එක, ඒ දෙක අපි කම්පෙයාර් කරොත් අපිට කම්පෙයාර් කරන්න පුළුවන් ඒ දෙන්නගේ මැග්නිටියුඩ් එකනුයි ඩිරෙක්ෂන් එකනුයි. ඒතර අයිගන් වෙක්ටර් එකක් අපි මෙයාට දුන්නොත් කියන විශේෂත්වය තමයි මේ මැට්‍රික්ස් ප්‍රොඩක්ට් එකේදී මෙයාගේ ඩිරෙක්ෂන් එක අපි වෙනස් කරන්නේ නැහැ. එයාගේ වෙනස් වෙන්නේ එයාගේ මෙයාගේ මැග්නිටියුඩ් එක විතරයි ඒත් මේ ලැම්ඩා amount එකේ මොකද වෙක්ටර් එකක් මොකක් හරි තාත්වික සංඛ්‍යාවකින් වැඩි වුණාම වෙන්නේ ඒ වෙක්ටර් එක තියෙන මැග්නිටියුඩ් එක විතරයි වෙනස් වෙන්නේ ඩිරෙක්ෂන් එක වෙනස් වෙන්නේ නැහැ මම හිතනවා ඒක පැහැදිලි කියලා අයිගන් වැලියු එක කියන පැහැදිලි කියලා මම හිතනවා right මොකද අපි ඕනම වෙලාවක කියන්නේ ඔයාට කියන්නේ තවත් මේක පැහැදිලි කරලා කියනවා නම්
එතකොට තන ඒක කියන්නේ වෙක්ටර් එක ට්‍රාන්ස්ෆෝම් කරන එකද මොකක් හරි
ඒක මැට්‍රික්ස් එක. ඒ කියන්නේ ඒක කියන්නේ ඕනම මැට්‍රික්ස් එකක්. ඔයා මොකක් හරි අපි මොකක් හරි ඔයාට න්‍යාසයක් අරගෙන එයාව වෙක්ටර් එකකින් වැඩි කරන්න පුළුවන් නේ. ඒ කියන්නේ ඕනම ස්ක්වයර් මැට්‍රික්ස් එක. that ස්ක්වයර් කියලා හිතාගෙන යන්න. මොකද නැත්නම් අයිගන් වැලියුස් ගන්න අමාරුයි මේ ස්ක්වයර් ඕන මැට්‍රික්ස් වල. ඒ කියන්නේ ඕනම ස්ක්වයර් මැට්‍රික්ස් එක. ඊතන ඔයාගේ වෙක්ටර් එක n+1 වෙක්ටර් එකක් නම් ඔයාගේ මැට්‍රික්ස් එක n times n වෙනවා. ඒක වෙක්ටර් ට්‍රාන්ස්ෆෝර්මේෂන් එකක්ම තමයි මෙතන වෙන්නේ. අපි ලීනියර් ට්‍රාන්ස්ෆෝර්මේෂන්ස් වල කතා කරනවා. ඔයාට වෙක්ටර් ලීනියර් ට්‍රාන්ස්ෆෝර්මේෂන් එකක් වෙක්ටර් එකක් විදිහට ලියන්න පුළුවන්. හැබැයි මෙතන ඒ කියන්නේ ඕනම වෙක්ටර් එකක්. එතකොට ඒක එක්තරා ආකාරයක වෙක්ටර් ට්‍රාන්ස්ෆෝර්මේෂන් එකක් තමයි. මොකද ඔයා එක වෙක්ටර් එකක් දෙනවා තව වෙක්ටර් එකක් එළියට එනවා. ඔයා හිතපු විදිහ හරි. හැබැයි ප්‍රශ්නේ තියෙන්නේ මේ දෙනගේ ඉන්පුට් එකයි අවුට්පුට් එකයි කම්පෙයාර් කරනකොට ඔයා දන්නවා වෙක්ටර් එකක් වෙක්ටර්ස් දෙකක් කම්පෙයාර් කරන්න පුළුවන් ඒ දෙනගේ මැග්නිටියුඩ් එක නෙවෙයි ඩිරෙක්ෂන් එක. මොකද මැග්නිටියුඩ් එක ඩිරෙක්ෂන් එක විතරයි ඒ දෙනට දෙන කැරක්ටරිස්ටික් දෙක. එතකොට ඔයාට වෙක්ටර් ට්‍රාන්ස්ෆෝර්මේෂන් එකක් කරාට පස්සේ ඔයාට හම්බෙන වෙක්ටර් එකේ මැග්නිටියුඩ් එක වෙනස් වෙන්නත් පුළුවන් ඩිරෙක්ෂන් එක වෙනස් වෙන්නත් පුළුවන්. ඒතර අයිගන් වැලියු තියෙන විශේෂත්වය තමයි එයා මැග්නිටියුඩ් එක වෙනස් කරන්නේ නැහැ. පැහැදිලි?
හරි.
ඒක අපි තවත් විදිහක් කිව්වොත් නිකන් මම උදාහරණයක් විදිහට ගන්නම් මේක ඕනම් වෙක්ටර් ට්‍රාන්ස්ෆෝර්මේෂන් එකක් විදිහට මම x කියලා වෙක්ටර් එකක් දෙනවා මට v කියලා වෙක්ටර් එකක් එළියට එනවා. හිතන්නකෝ මම දුන්නේ මෙහෙම වගේ වෙක්ටර් එකක් x කියලා හිතන්න මෙයාගේ මැග්නිටියුඩ් එක 1 විතර මම ඔරිජින් එකට සාපේක්ෂ පොසිෂන් වෙක්ටර් එකක් විදිහට ගත්තොත් මට හම්බෙන්නේ මෙන්න මේ වගේ වෙක්ටර් එකක් v කියලා මෙයාගේ මැග්නිටියුඩ් එකත් 1. හැබැයි එයා කැරකිලා පොඩ්ඩක්. ඒ කියන්නේ එයාගේ ඩිරෙක්ෂන් එක වෙනස් වෙනවා. ඒ කියන්නේ අපි සමහර වෙක්ටර් ට්‍රාන්ස්ෆෝර්මේෂන්ස් තියෙනවා මෙයාගේ කියන්නේ මොකද්ද මැග්නිටියුඩ් එක වෙනස් කරන්නේ නැහැ. එයා වෙනස් කරන ඩිරෙක්ෂන් එක. ඒ වගේ ඒවට අපි කියනවා රොටේෂන්ස් කියලා. මම නිකන් ජස්ට් අයිඩියා එකක් දෙන්නේ. ඊට පස්සේ තව ඒවා තියෙනවා දැන් ඔය අයිගන් වෙක්ටර්ස් වගේ සමහර ට්‍රාන්ස්ෆෝර්මේෂන්ස් තියෙනවා මෙයාගේ අවුට්පුට් එක මට හම්බෙන්නේ මෙයාගේ ඩිරෙක්ෂන් එකටම තියෙන වෙන වෙක්ටර් එකක්. මොකද ලැම්ඩා x ඒ වගේ එකක්. උතර මේකෙදි වෙන්නේ මේක ඇත්තට වෙන්නේ ඩිරෙක්ෂන් එක සමානයි. මේක කන්ස්ටන්ට්. හැබැයි මැග්නිටියුඩ් එක වෙනස් වෙනවා. මේක එහා පැත්තට යන්න පුළුවන්. ඒ කියන්නේ ඔන්න නෙගටිව් පැත්තට යන්න පුළුවන්. ඒක ප්‍රශ්නයක් නැහැ. ඒතකොට කියන්නේ එකම පැත්තට මයිනස් වැලියු එකක් આવොත් අයිගන් වැලියු එකට. ඊට පස්සේ තව ඒවා තියෙනවා. දැන් ඕනම ජෙනරලයිස් ට්‍රාන්ස්ෆෝර්මේෂන් එකක් ගත්තොත් කියන්නේ මේ දෙකේ එකතුවක්. ඒ කියන්නේ ඔයා ඩිරෙක්ෂන් එකත් වෙනස් කරනවා එකපාර එයාගේ කන්ස්ටන්ට් මේ එයාගේ මැග්නිටියුඩ් එකත් වෙනස් කරනවා. If you get any vector transformation, at the end of the day, you give some vector and you get some vector. If you compare both input and output, sometimes you can have both input and output having the same magnitude but changing directions. Those kind of transformation we call rotations. And sometimes we have, when you compare the both input and output, we have the same direction but different magnitudes. These types of time actually, if you say if your vector transformation is something like ax, those type of vectors we call it is a eigen values, because if you give some inputs to this vector product as a vector x and we output something like lambda x, it means it doesn't change the direction, only the magnitude, so it is an eigen vector. So this is the idea of eigen vector. It is clear? Is it clear or you need more explanation on that? Hello? Is it clear?
Oh, yes.
Okay. So then you can have something like this. You can have, let's say that now you have to find, let's say you have this matrix, like because you have something, let's say, I'm not going to write in this, let's say I write some vector. Let's say it is 4, 0, 4 and 0, 4, 4 and 4, 4, 8. This is my vector. So I need to find this guy's eigenvectors. Let's say my eigenvectors, I need to find eigenvectors. It means which vectors, if I multiply by those vectors with this matrix, which gives the same direction, and also I need to find eigenvalues. Okay. So this is, let's say this is lambda x. If we get that thing, this thing we called eigenvalue. It means it means if you give the vector x, if you output lambda x, this constant you called eigenvalue, and this vector you called eigenvector. So you need to find what are these eigenvectors and what are those eigenvalues. So there should be a way to find it. First, you take this equation. Let's say ax equals lambda x. So then what I do is I write something like this. Ax equals lambda times, instead of x, I write ix. Okay. So then I can take this to this side. I can get ax minus lambda ix equal to 0. So I can write a minus lambda I x equal to 0. This is I is nothing but identity matrix. Identity matrix is nothing but if you say 3 by 3 identity matrix, it is something like this: 1 0 0 0 1 0 0 0 1. Only this diagonal element has ones, others are zeros. So then it means if you get this equation, because this is my equation, so this thing is the equation. So from using this thing, I can find my eigenvalues and eigenvectors. So then let's say this is x is non-zero vector. Okay, x is non-zero vector. Why? If this is a zero vector, let's say x is something like 0 0 0. Anyway, we know ax equals 0 0 0. You can put any constant here, it will become eigenvector. So x equals 0 vector, there's no point talking something like this, because if x is 0 vector, both sides become 0. Anyway, trivially, the equation holds. So we need to find non-zero vectors which is satisfy this criteria. So we need to find a solution or find a system where this x is non-zero values. So we know from our equations knowledge, if say ax equals b 0, this equation said if this a's determinant equivalent to 0, right? If a's determinant equivalent to 0, the system has non-zero solutions. Okay, because if it is not equal to 0, you only have the 0 vector as a solution. It means ax සමාන බිඳුවක ප්‍රොඩක්ට් එකක් ගත්තට පස්සේ ඒකේ ඩිටර්මිනන්ට් එක 0 නෙමෙයි නම් ඔයාට non-zero solution එකක් මෙයාට තියෙන්න බෑ. මේක අපි කතා කරා linearly independence එක කතාවේදී මම මේ solutions හොයන ගැන කතාවක් කිව්වා. දැන් මෙතන මම කතා කරන්නේ Gaussian elimination එක ගැන නෙමෙයි determinant එක ගැන. right? මෙයාගේ determinant එක කියනවා determinant එක 0 නෙමෙයි නම් ඔයාට solutions තියෙනවා. මේක ඕගලන්ට ඕන geometrical interpretation එකක් තියෙනවා කොහොමද මේක වෙන්නේ කියලා 2D වලට මම මේක මෙතන කතා කරන්න යන්නේ නැහැ. නමුත් දැනට මතක තියාගන්න සාමාන්‍යයෙන් ඕගලන්ට ax equals 0 කියනවා right hand side එක 0 වෙනකොට මේ 0 කියන මෙතන 0 vector එක ඒ වගේ vector equation එකක් ගත්තොත් එයාට non zero solution එකක් තියෙන්න නම් අනිවාර්යයෙන්ම මෙන්න මේ matrix එකේ determinant එක 0 වෙන්නම ඕනේ. හරි? ඒ කියන්නේ මෙන්න මෙතන this should be 0, right? So then it means this a minus lambda I think, right? So this is determinant should be equivalent to 0. You can put these two bars. It means you can evaluate this thing. It means this is equal to 4 0 4 0 4 4 and 4 4 8, and this is minus lambda times 1 0 0 0 1 0 0 0 1. So you can write this thing as simply, you can write this thing as, it's pretty much easy. You only have to subtract lambda from diagonal elements. Others are not changing. So this is 4, okay, and this is 4 4 8 minus lambda. Then you know how to find the determinant of this. So this is actually determinant 4 minus lambda times determinant of 4 minus lambda. 4 minus lambda times 4, and you can have 4 times 8 minus lambda, and you can have plus 0 times, you don't have to worry about what is this coming here, and 4 times you can have the determinant 0 4 minus lambda and 4 4. Okay, so then you can easily find this thing is equal to 4 minus lambda times 4 minus lambda 8 minus lambda minus 16 and plus 4 times 0 times 4 is 0 minus 4 times 4 minus lambda, and you can equal this to 0. Then you get some polynomial equation and you can get factoring and you can find the what are these corresponding eigenvalues are. So if you find properly these eigenvalues, actually I write a MATLAB code just a while ago, you will get eigenvalues as actually, oh, if I solve this, right? If you need, I can solve that. So I think it is not a big issue. We can just solve it by this. We can get 4 minus lambda times 4 minus lambda times 8 minus lambda minus 16 4 minus lambda, and we can have minus 16 4 minus lambda. This is equal to 0. So we can take 4 minus lambda out. Then we can have 4 minus lambda minus 8 minus lambda. This is minus 32. Okay. So this is the thing you can have. Then you can have this equal to 0. Then you can have 4 minus lambda times 32 minus 8 lambda minus 12 lambda minus 32 equivalent to 0. This is actually 32 lambda plus lambda squared. So lambda squared minus 32 equal to 0. So then you can have 4 minus lambda times lambda squared minus 12 lambda, which is equal to 0. Then you can have 4 minus lambda times lambda minus 12 times lambda equal to 0. Then you can have the eigenvalues are 0, lambda equals 4, and you can have eigenvalues as lambda equal 12. So these are my eigenvalues. Okay. So first, in any problem, if you're given a matrix, I give you a little trick, right? So you don't have to memorize all these things. You have to just write to a matrix as it is. First, you can have to write matrix as it is. Then you have to actually, let's say this is your matrix. You have the matrix of 4 0 4 and 0 4 4 and 4 4 8. Then you can subtract lambda, some constant, from the diagonal, and then you can evaluate the determinant treating lambda as some variable. Then you can equal this determinant to a 0. Then you can solve for lambda. You will get the eigenvalues. I think that part is clear. Hello. Okay. Is it clear? How you find it? You don't have to memorize anything. If you give any matrix, they say if they say you to find eigenvalues, you have to just do this. But this is the theory behind it. I just explain it for your convenience. But if you want to find it, this is the simple way. Okay. For the mid, you can easily calculate. And then I saw some simple Python code. You can do it yourself. I think it is open book and open it exam. I think you can do that to find the answers using like NumPy programming language, right? So I think if it is allowed, right, or if it is allowed only, but is it allowed to use programming tools? Hello? Hello? Is it allowed to use programming tools? Because I just saw some mathematical script. That's why I'm asked, right? Hello?
Yes, sir, we can use.
So, okay. So I will explain how to do it with Python, right? So because previously actually I did with MATLAB. Today actually I first time wrote a code to find these eigenvalues in NumPy, because if you open in MATLAB in exam time, it will sometimes your PC can stuck. So you can use NumPy package in MATLAB. I will show how you can do that in Python as well. So it is pretty much easy. So you can just open a Jupyter notebook and yeah, I will probably share a tutorial how to set up a Jupyter notebook in Visual Studio, or set up Jupyter notebook. It is pretty much easy. You have just download and run. Then you can easily calculate any of the eigenvalues, or else you can use Google Colab, because if you save this notebook, and you can just have to change the values and get the answer. Okay, because if it is allowed, that's fine, but because it is not like cheating, right? You write the code. Okay, so then that is how it can be done. Then okay, now let's say that now we have two solutions, right? We have lambda equals 0, lambda equals 4, and we have lambda equals 12, right? So these are my three eigen values. Okay. So then actually 0 means actually 0 means this. If you have some vectors, this system should have non-zero eigenvalues. It means these systems, if you write the determinant of this system, it is also equivalent to 0. It means 0 is as eigenvalue means the original system, let's say ax equals 0, it should have this determinant equivalent to 0. It means this system has non-zero solution which satisfy this criterion, this equal to 0 vector. So that's why you get 0 as an eigenvalue. So then you have to find out what are my eigenvalues are. Okay, so then I will first use lambda equals, let's say 0, because it is easy. So what you have to do is my equations then become 4, 0, 4, 0, 4, 4, 4, 4, 8. This is my equation become. I just write my eigenvalue as x1, x2, x3, which is equivalent to 0. So then probably you can use Gaussian elimination to find what my these x vector are. Because when you find these eigenvectors, right, you can treat this equation. Right? This is the equation I need to solve for which lambda values I will I have non-zero solutions. So once you have lambda, this is become regular solving problem. ඒ කියන්නේ දැන් අපිට හොයන්න ඕනේ මෙන්න මෙයාට සොලියුෂන් එකක් තියෙනවා. අපි දන්න මෙයාගේ සොලියුෂන් එක තමයි x කියන එක නමයාගේ සොලියුෂන් එකක් නම් එයා අයිගන් වෙක්ටර් එකක්. ඒතර මම හොයන්න යන්නේ x කියන එක්කෙනාට non zero වෙක්ටර් එකක් එන්නේ ලැම්ඩාගේ මොන අගයන්ටද කියලා මම මේ දැන් ඉස්සෙල්ලා හෙව්වේ. ඩිටර්මිනන්ට් එක 0 කරලා. දැන් ලැම්ඩා ටික හොයාගත්තට පස්සේ ඒ එක ලැම්ඩාට මේ වගේ සිස්ටම්ස් එක ගානේ තියෙනවා. එතකොට මම ලැම්ඩාව මෙතනට සබ්ස්ටිටියුට් කරලා මේ සිස්ටම් එක විසඳුවොත් මට හම්බෙන්නේ අන්න ඒ ලැම්ඩාට අදාළ x කියන වෙක්ටර් එක මගේ අයිගන් වෙක්ටර් එක. දෙක පටල ගන්න එපා. මුලින්ම මම කරන්නේ අයිගන් වෙක්ටර් එක සැටිස්ෆයි කරන්න ඕන ඉක්වේෂන් එක මේ විදිහට ගන්නවා. ඊට පස්සේ මගේ අයිගන් වෙක්ටර් එක අපි කියන 0 කියන එක නම් කොහොමද ට්‍රිවියල් හින්දා non zero වෙක්ටර් එකක් මෙයාව සැටිස්ෆයි කරනවා නම් ඒ වෙලාවටම තියෙන්න පුළුවන් මොන වගේ ලැම්ඩාද කියලා මම උපකල්පනය කරලා මුලින්ම හොයනවා ලැම්ඩාව. කියන අයිගන් වැලියුස් ටිකම. අයිගන් වැලියුස් ටික හොයාගත්තට පස්සේ ඒ අයිගන් වැලියුස් පාවිච්චි කරලා ඒ අයිගන් වැලියුස් එක මෙතන සබ්ස්ටිටියුට් කරාට පස්සේ මට ආයි හම්බෙන්නේ මෙයා මොකක් හරි මේට්‍රික්ස් එකක් වෙනවා b වගේ. එතන මට මේ ඉක්වේෂන් එක bx 0 වගේ. එතන මම දැන් b කියන්නේ මම දන්න වෙක්ටර් එකන්නේ. මේ මේට්‍රික්ස් එක ගන්න මොකද මම ලැම්ඩාව දන්නවා නම් මම දන්න යුනිට් මේට්‍රික්ස් එක මම දන්නවා මගේ a කියන මේට්‍රික්ස් එක මම දන්නවා මේ සිස්ටම් මේ b කියන මේට්‍රික්ස් එක මොකක්ද කියලා. මට මෙයාව සෝල්ව් කරලා x හොයනවා කියන්නේ x කියන්නේ අර මගේ ලැම්ඩා අගයට අදාළ අයිගන් වැලියු එක. ඒ කියන්නේ මුලින්ම කරන මුලින්ම ලැම්ඩා ගයන් ටික හොයාගෙන මේ එක ලැම්ඩා ගයන්ට මෙන්න මේ ඉක්වේෂන් එක මෙන්න මෙයාව ඕගොල්ලෝ සෝල්ව් කරන්න ඕනේ. ඔය දෙක පටලවා ගන්න එපා හරි. මම ගොඩක් අය ඔක පටලවා ගන්නවා. මෙයාව තව x1 x2 x3 මෙන්න මෙයාව සමානයි 0 එකට එක් කරලා මෙන්න මේ set of equation එක ඕගොල්ලෝ solve කරන්න ඕනේ. It means for any lambda value you find or any eigen value you find, you should solve this system of equation to get this x1, x2 and x3 or your x vector to get an eigen value. Okay. I perform a Gaussian elimination on this system of equation because lambda equals 0 means you have nothing to subtract from these diagonal values. So I will perform Gaussian elimination. So I can write this thing as 4, 0, 4, 0, 4, 4, and I can have 4, 4, 8, and I can have my right hand side, it is 0. So then what I can do, I divide my row 1 by 4. So then I can have 1, 0, 1, this is 0. Then I divide my, I can write 4, 4, and 4, this is 4, 4, 8, okay, 0, 0. So this is things. Then I divide my row 2 by 4 to make this element 1 because this is already 0, so I have to make this one. So then this simple Gaussian elimination 0, 1, this is 0. Now I can have 0, 1, 0, sorry, 0, 0, 1, 1, and this is 0. Okay. So then I can have 4, 4, 8 because I did nothing to my third row. So then to my third row, what I can do is I want to make this 0. So I can have my row 3 is equal to row 3 minus 4 times R1. So I can have 1, 0, 1, 0. I can have 1, 0, 1. And then I can have 0. If I time 4 times, it is 4. And this is 4 times, it is 4. It is 0. You can clearly see that once you remove that, this is become exactly the 4 times my row 2 because this is why this is determinant becomes 0. So I will explain that to you later. So then I remove my row 4. It means 4 times row 2 because I want to make this element 0. So then I will end up as this vector 1, 0, 0, 0, 0, and this is 1, 0, and this is 0, 0, all zeros, right? So it means I can write the resulting equations as x1 plus x3 equivalent to 0 and x2 equivalent to 0. So this is my resulting equation. So in this area, I cannot have anything, right? So because it is just 0, 0, 0, it means it is actually, if you write the equation, it means 0x1 plus 0x2 plus 0x3 equivalent to 0. It is actually trivially, right? It is trivially hard. So it is no use to solve this equation. So here, actually, we can put x2 equals 0, but we have this criterion. So we have x1 and x3 because we have two equations. We have to find three variables. So straight away we can see x2 equals 0. So x1 and x3, we only have one equation, but we have to find both x1 and x3. So what we have to do is I just substitute x3 equals t some parameter. Then I can get x1 equals minus t. So I can write my solution vector x vector as x1, x2, x3. It is my solution vector. It is actually, I can write, it is minus t, 0, t, and I can write this thing as minus 1, 0, 1 times t, or you can take t forward if you want, right? No matter how you write, it is t. So this is my eigenvalue, sorry, eigenvector. Eigenvector correspond to lambda equals 0. Okay, so I think I will show you how Python script work. I think I didn't mess up that one. Okay, so this is my eigenvector. So minus 1, 0, 1. Okay, so then actually, yeah, this should be, I think, yeah, I did not do anything. Yeah, so basically that are my eigenvectors. Okay, so okay, I think I didn't do anything wrong, right? So this is my equation. Oh, sorry. Yeah, this is my equation. So this is my eigenvector, which I can correspond to lambda equals 0. So then I have to find my eigenvectors to correspond actually lambda equals 4. I need to find what is my eigenvectors correspond to lambda equals 1. Okay, so then I have to find this thing as well. So basically, I need to find my eigenvector correspond to lambda equals 4. Then what I have to do, I have to solve this equation. Instead of this equation, I have to solve 4 minus 4, and my vector is actually 0, 4, and 0, 4, 4. I have to find, I'm not going to solve it before completely, right? It is actually 0, 4, sorry, 4, 4, 8 minus 4, right? So this is times x1, x2, x3. You have to find which values of x1, x2, x3 gives 2 gives as the 0. So if it is, if it will come some as sort of a vector, you can do the same thing, because you can have to use some parameter, because anyway it is gonna give some set of equations which is less than 3 equations. So you have to use some parameter and do the same thing and get the eigenvector here. Fine? Hello? Is it fine, or you need to explain more detail in that? Hello? Hello? Okay, so okay, so these are things you can do because this is I think several reasons I have to find out. I think there should be some there's some difference between the answers I got from the Python code and this. That's why I double check it. I think I did not do any mistakes when solving this, right? I just do the things correctly, I think. Yeah, I think okay, because I think it is I will just check back and see in the code as well. Okay, okay, so then this is my eigenvalue. So it is actually, there's nothing wrong in the calculation. See, I think it is something bug in the code. Okay, so then you know what are the eigenvalues and eigenvectors are. So then what you have to do, you have to solve each type of equation. Sometimes you will get let's say you have 3 parameters, you didn't get this equation at all, right? So if, let's say this is x2 equals 0, you only get the first equation. Let's say you only get this equation at the end, and you didn't get the second equation at all. So then what you have to do is you have to, let's say this x3 equal to 0. You only have the equation is x1 equals minus x3. So you have to use two parameters. Let's say you use x2 equals t, x3 equals u or something. Then you can have x1 equals minus u, x2 equals t, sorry, x2 equals t, and then you can have x3 equals u. So then you can write your vector, solution vector x2, x3 is something like this. It is actually minus u, 0 u, plus 0 t 0. This is, you can write u times minus 1 0 u, 1 plus t times 0 1 0. It means any combination of these two vectors will work as your solution because you have to use two parameters. In this case, let's say it is equal to some, let's say this is some hypothetical case, it is equal to some lambda naught value. So this lambda naught value, you have two eigenvectors. Okay, if you put this thing, also it will give lambda naught times minus 1 0 1 as the output. Also you can have if you put this vector, it is also give output as 0 1 0, or any linear combination between those two vectors, you will get the output. You will see why next. If you get things clearly, hello, fine, hello, hello, because I will explain, because let's say forget about that part as well. Let's say you have these two solutions, right? It means because some lambda naught value, let's say some lambda naught value, you have these two solutions to a particular vector equation, the linear equation. Then you have one eigenvalue, but correspond to that eigenvalue, you have two eigenvectors. Let's say it is something like this. It means you have ax1 equals lambda naught x1. And also you have ax2, it is also lambda naught x2. Okay. So then you will give some, consider something like this. Let's say ux1 plus tx2. This is equal a times ux1 plus a times tx2, because t, u and t are real numbers, right? So you can take them out. You can write ax1 plus, you can take t out, ax2. Then you can write this thing as u times lambda naught x1 plus t times lambda naught x2. So you can take lambda naught out. This is actually ux1 plus tx2. It means in such a case, something like this, if you have one eigenvalue, but you have two vectors as a solution, what will happen is any linear combination of these two eigenvectors have the same eigenvalue. Okay, fine. You got the point? Because this is the same vector as this. Hello.
Yes, I got.
Okay, so this is the actually about the eigenvalue. I just show. I will show you the Python script how you do. I think I mess up with some indexing, right? Okay, so you have to, when you do Python, I think, hope you get my screen, right? Okay, hope you might get my screen. You have to import numpy. If you don't have numpy, you can write pip install numpy, so you can easily install that package. So then you can define a matrix, something like this. You can have np.array. These are my rows of the matrix, right? These are my rows of the matrix. And you can have separate a comma, and you can have one square brackets and another square bracket. This is my one row, and this is my another row, and this is my third row. So then this is my matrix, look like 4 0 4 0 4 4 and 4 4 8. This is my matrix. Then you have to find, let's say, this is just how you perform matrix multiplication. Let's say you have to multiply this vector by 2 8 9. So then what you have to do is you have to define a vector. It is np.array. So it is actually, definitely if you define like this, it will take as a column vector. So then you have to perform the matrix multiplication. You have to perform np.matmul a comma u. So it will perform this matrix multiplication and give this as my answer. Because if I if I get the matrix multiplication 4 0 4, if you multiply this one, it is 8, and 36, it is 44, and you can get easily the answer. This is a column vector, right? This is not a row vector, this is a column vector. So then if you want to find the eigenvalues and eigenvectors, you have to find E comma V. This is E is the one which stores the eigenvalues. these are the one we store the eigenvector. So you have to use np.linalg.eig.a. So it will output so this E vector. These are the my eigenvalues. So E means this one, right? The first thing is my eigenvalues. This array means 12, 4. This actually pretty much high negative values is 10 to the power minus 16 means actually this is like 0, right? Because in numerical computation you have slightly bit of errors due to approximation. So this is actually 0, right? That's why it is become very low value. So then these are my eigenvalues. So these columns are my eigenvectors. Actually, I'm not sure about whether it is this one or this one. I have to check on that. I think it is this one, right? I think it is this one. I better check it. In MATLAB, it is actually the columns. I'm not sure about the NumPy. I will just let you know at the So anyway, you will get this matrix. This is the matrix containing my eigenvectors. Most probably, I think it will be columns, right? These things are my eigenvectors. So then you can actually I can test because I just get the multiplication of my matrix and my first second eigenvector. It means this one, right? So if I get the my second eigenvector, so then this is my answer. So to confirm it, I get the eigenvalue correspond to it and multiply it by this eigenvector. I get this as the answer. Okay. So this is how you can do. I will like share you script and some tutorial on that. You can easily calculate. Actually, these are the commands you need to know. So then you can easily compute. In MATLAB, I think it is pretty much easy, right? It is pretty much straightforward. MATLAB, it is sure that these columns are the eigenvectors. I think here, there's some round of errors are there. That's why it is values look like somewhat different than what we obtained. But if you properly do the calculations, you can easily see what are my eigenvalues are. Fine. Hello. Is it okay? Hello. Fine.
Okay. Yes.
Okay. So these are the things I need to highlight to you again, the eigenvalues. So then we can move into the diagonalization. Okay. Diagonalization, you need to understand what is this really, because in diagonalization, it is the key thing to based on actually the QR factorization and also the what you call singular value decomposition, SVD. So actually, I'm not much do in this singular decomposition. Actually, I just show how you to do it. But if you understand the theory well, you can do probably, because in MCQs you can ask some theory stuff. So I think most probably that will ask, because I didn't see any sort of values so like real the notes you send to me, like pretty much high level one. Okay, so let's say something like this. So I have my, let's say a vector, a matrix. Let's say it is a 3 by 3 matrix. Let's say this has 3 eigenvectors and we have 3 eigenvalues. These 2 eigenvalues can be same, right? So now if this has 3 eigenvalues, most of the times these eigenvalues are orthogonal. Orthogonal are linearly independent, right? Most probably these two, I think it is, I don't remember it is a theory or not. I think most of the time it will be orthogonal or linearly. It is sure it is linearly independent, but I'm not sure about the orthogonality. I think most probably they will be orthogonal sometimes, but anyway, it is linearly independent matrix, independent vectors. So then what you can do is you have three eigenvectors and you have 3 eigenvalues. Okay, it means, let's say you have, I denote these eigenvectors as E1, E2, and E3. So you have AE1 as lambda E1, sorry, lambda 1 E1, AE2 as lambda 2 E2, and you can have AE3 as lambda 3 E3. So then I just consider this matrix. Okay. Let's say I have E11, E12, E13. I explained this notation before. A22, A23, A31, A32, A33. This is actually nothing but the I write just this is my first eigenvector as a column vector, right? This is E1, and this is my second eigenvector as a column E2, and this is my third eigenvector as a column E3. So these are my eigenvectors. I just write a matrix using my 3 eigenvectors. I put my eigenvectors as column of this matrix. Let's denote this as P. Now I consider the matrix product AP. Okay, I consider the matrix product AP. If I do this matrix product AP, you can clearly see that, because if you multiply with this AP product, it means the first column you get as the answer. First column you get as the answer, it means you multiply, if you multiply by this A matrix by this one, it means you multiply this vector with matrix A, you will end up with the first column of this answer. Because every time you get one row and multiply with this one to get this element, and you get the second row and multiply by this row, this column to get the second element, and you get this row and multiply this column to get this element. It is nothing but multiplying this E1 vector with this matrix. It means you will end up lambda 1 E11, lambda 2 E22, lambda 3 E12, 1 3, and at the same time you can have this one as well, lambda 2 E22, lambda 2 E23, and this lambda 3 E31, lambda 3 E32, and lambda 3 E33. This is nothing but, because you can see when you perform matrix multiplication, what you do is you take a row of this and multiply with the column of this. So if you consider only how this first column come, it will nothing but the matrix and the vector E1's matrix product. So if I concatenate this matrix in a way like this, let's say E1, E2, E3. This idea is these are column vectors, like I write as column vectors, and I can write the same notation as this, right? Instead of writing this column as 3 elements, I just write as E1 vector. It means my first column is my E1 vector. So my second column is E2 vector, and my third column is E3 vector. So this is the notation. So if this matrix product, I can write it as lambda 1 E1, lambda 2 E2, and lambda 3 E3. So this is my matrix product after my matrix multiplication. So then what is the importance of this? Now, let's say for a moment, E1, E2, and E3 are orthogonal. Okay, and each of these norms is equivalent to 1. So let's see what happened. Orthogonal means EI, EJ, if you compare this dot product, is equal to 0 when I doesn't equal to j. It is only equal to 1 when I equivalent to j. Okay, it means if you take the dot product between any of these two vectors, it is only become 1 when you get the dot product with the vector itself. It means E1 dot E1 or E2 dot E2 E3 dot E3. If you get the dot product like E1 and E2 or E3, it will become 0. So for a moment, see this hold. So now what will happen if you take my P matrix and get the transpose? My P transpose would become E11, E12, E13, E21, E22, E23, E31, E32, E33. This is nothing but I place my eigenvectors as rows. Okay. Now look at very carefully, right? Now look very carefully. Now I have this. Okay. I have this. Now I consider the vector product PT times P. This is nothing but, in these cases, I have this first row as my E1, and this thing I have my E2 vector, and this is E3 vector. And I have to get the matrix product with, now my columns in the second matrix, I have columns as E1, E2, and E3. So now, when you take in a matrix product, it is nothing but you consider first matrix row as a vector and second matrix column as a vector and get the dot product between those two vectors. So you can clearly see if you evaluate this thing, because we have this condition, right? It is only become 1 in the diagonals. Why? Because if you take E1 and E1, it will become 1. And if you consider other two elements, E1 and E2 decompose 0, and E1 and E3 become 0. And if you now you back to the second row, if you dot product with this E2 column, So the first column, it will result 0, but the second column results 1, and third column results 0. And the same go to the third column as well. So why this happens, the importance of this is, if you are eigenvalues, or if you have some matrix, right? If your matrix, if you have some rows, either rows are orthonormal, it means they are both orthogonal and their magnitude is 1, or their row are orthonormal, it means their rows, if you consider them as vectors, they are orthogonal and their norm is 1. If these conditions are satisfied, their inverse is nothing but their transpose. You get the point? Hello? You get the point? Hello?
Yes, sir.
Not sir. Yeah.
Yeah, you know.
Okay. So, okay. So then it means, what is the importance of this? Okay. So basically, if you have, let's say, I explained that as well. Let's say you have some vector A times V1 equals lambda 1 V1, right? So you just put the vector V1 divided by V1's norm and multiply by A. You will end up, you can get this norm out because it is just a real number. Then you have AV1, and then you can have V1's norm, and AV1 is nothing but lambda 1 V1. So you can have lambda 1 times V1 divided by V1's norm. So you can actually normalize your vectors, your eigenvalues won't change. Okay. So you can normalize your vectors, your eigenvalues won't change. Fine. Hello. Is it fine? Hello. Fine. Okay. So now we have to find what is the importance of this thing. Okay. Yes. Now we have find out that let's say something like this. If we get the matrix product A, P, right? A, P, we get the matrix product. We see that it is something like lambda 1 E1 and lambda 2 E2 and lambda 3 E3. Something like this. Now I get multiply this one P1 A P. It is P1 inverse means nothing but I have something like this E1 vector, E2 vector, E3 vector. It means in this matrix as rows I have my eigen vectors. So in the second one I can have lambda 1 E1, lambda 2 E2 and lambda 3 E3. So these are my columns, right? These are columns, right? These are you probably see in this way, these are columns and these are rows, right? So if you consider this product, you can get lambda 1 E1 times lambda 1 E1 means, you know, E1 dot product E1 is 1, you will end up in lambda 1. But you get the second element, E1 dot product E2 is 0 and E1 dot product E3 is becomes 0. And you move into second row, it is my eigenvector E2. If I dot product with E1, because the column is lambda 1 E1, I can take lambda 1 out, it will result 0. But if I do for this same thing to the second column, it will result lambda 2 and other one results 2. In the same way, you can get this one lambda 3. This is we called diagonalization matrix. Diagonalized matrix or diagonal matrix. Okay. Usually we denote it as D. It means if a problem given to you, given some matrix, and this if you are told to diagonalize this matrix, first you have to solve the now I explain the shortcut. So now you know how this comes, right? If you like confuse these things, just forget about it. This thing will not be asked in the exams, but you need to know what will happen is this, because I tell this is because the next thing I tell you to know is how to do and how to write P matrix and how to write this diagonal matrix at once, because you need to know how you choose this lambda 1, lambda 2, lambda 3 and E1 and E2 and E3. First you have to do is something like this, because this we call diagonal matrix. So in problems, what you have to do is, what you have asked for is, you have given some matrix A and you are told to find diagonalization. It means you need to find this P and D. Okay. So first you have to find this before writing these two, you have to find, let's say this is 3 by 3 matrix for simplicity. You have to find 3 eigenvalues, because you have to, if you want to diagonalize, this should have 3 eigenvalues, or at least sometimes this can have 2 eigenvalues, let's say lambda 1 and lambda 2, but these 2 eigenvalues can result 3 eigenvectors. Okay, because same eigenvalue can result more than one eigenvalue, eigenvector. So to diagonalize the matrix, n by n matrix, you need to have n eigenvectors. Without n eigenvectors, you cannot diagonalize. Okay. So then you have to write this P vector. The key finding vector is you have to write your eigenvectors as columns. Right? And then you can write, let's say this is eigenvector correspond to lambda 1, and this is eigenvector correspond to lambda 2, and this is eigenvector correspond to lambda 3. If you write in this way, your diagonal vector becomes your first row belong to lambda 1, and second row belong to lambda 2, and third column belong to lambda 3. But if you shift this order, let's say you write, let's say I just pick another color, and say you write this column as lambda 2, and this column as lambda 3, and this column as lambda 1. Then your order will become, first row, it means instead of this element, you can have lambda 2. Instead of this element, you can have lambda 3. Instead of this element, you can have lambda 1. It means if your first column's eigenvector's eigenvalue is your first element here, and your second column's corresponding eigenvalue is your second element, and your third column's corresponding eigenvalue is your third item in your diagonal matrix. Fine. Hello. You got the diagonalization? How do you write it? The only thing you need to understand is how to find these lambda 1, lambda 2, and lambda 3 eigenvalues and eigenvalues. After finding this, you can write this matrix P by simply using them as columns. Okay?
අයියේ එතකොට ඔය eigen vectors අපි හදන්න නැතුව අපිට එකපාරට diagonalizable නැද්ද කියන්න බැරිද?
හදන්න නැතුව diagonalizable ද නැද්ද කියලා කියන්නට බෑ. මොකද ඔයාලට diagonalizable කියන්න නම් අනිවාර්යයෙන්ම ඔයාලට n by n matrix එකක් නම් eigen values n ගාණක් තියෙන්නම ඕනේ. හරි?
හරි.
මොකද සමහර matrices තියෙනවා eigen values 3ක් නැහැ කියන්නේ. diagonalization එක වෙනම කියලා තියෙන්නේ මම diagonalization වෙන්නේ නැති ඒවා තියෙන නිසානේ බං. ඒතකොට එකපාරට eigen values බලන්නේ නැතුව කියන්න අමාරුයි. හරි? හැබැයි eigen values හෙව්වට පස්සේ කියන්න පුළුවන් diagonalizable ද නැද්ද කියලා. පැහැදිලිද? හෙලෝ.
හරි.
දැන් ඒකනේ eigen values වලින් ප්‍රශ්නයක් ආවොත් සාමාන්‍යයෙන් ගොඩක් වෙලාවට eigen values වලින් අහන ප්‍රශ්නයක් තමයි මුලින්ම කියනවා matrix එකක් දීලා eigen values ටික හොයන්න කියනවා. ඊට පස්සේ කියනවා එයාගේ සාමාන්‍ය යන ඕඩර් එක තමයි එයාගේ eigen vectors ටික හොයන්න කියනවා. ඊට පස්සේ කියනවා මෙයාගේ diagonal matrix එක ලියන්න කියලා. ඊට පස්සේ සමහර item දෙනවා මෙන්න මේ වගේ එකක් හොයන්න. ඒ වල 1027 වෙනි බලයේ වගේ මහා තෘෂ්ණිම් භූත එකක් හොයන්න දෙන්න. හරිනේ? මේ වගේ හොයන්නේ මෙහෙමයි. දැන් අපි දන්නවනේ P AP inverse මෙයා සමාන වෙනවනේ D ට. අපි ඒක මෙතනින් හෙව්වනේ. මෙන්න ඉතින් මම පෙන්නුවානේ. මොකද මේ වගේ D කියන matrix එක මම මෙතනින් පෙන්නුවානේ. එතකොට A P inverse D ට සමාන වෙනවා. එතන මට මෙයාව ලියන්න පුළුවන්. I can write this thing as P A P inverse into P equal to DP, and sorry, it is not A, it is P, right? And this will become my identity matrix. So then this will become PA equals DP, and I can write P inverse PA is equal P inverse DP. So I can write this thing as because this thing is also my identity matrix, I can write A equals P inverse DP. Actually, these two identities, it's better to remember, or like you should be able to apply right away. Otherwise, you will be stuck in some exam type problems, right? It's better to write it somewhere. It is open book. Please note it down, these two equations. These are the only thing you need to memorize when dealing with eigenvector problems regarding to diagonalization. It is not to remember, right? If you remember this, you can easily get this one. Or if you remember what are the algebraic manipulation I do in the previous step, you can easily do that one. Anyone has a problem? I think Mike is on. Okay. So then you can do something like this. Then you can get the diagonalization vector, and this you have a vector like this. Let's say we need to evaluate a square. It means it is nothing but a multiplied by a. Substitute this one here, you can get P inverse P dP in P inverse dP. So this is become identity matrix. So this is just become P inverse D times dP. This is become P inverse D squared P. So the beauty of this diagonal matrix is, let's say you have something, diagonal matrix is something like this: 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. If we take the nth power of this, or we multiply this by n times, you will end up with this lambda 1 to the power n 0 0 0 lambda 2 to the power n 0 0 0 lambda 3 to the power n. It means you only have to take the power of the diagonal element. The resulting things are same. So if you have to evaluate this one, you need to do is P inverse, and you have to put your diagonal elements 10 to the power minus 1027 power, and you have to multiply by P. So then if you evaluate this product, because you can evaluate this straight away, just have to get the power of diagonal elements, and then you have to multiply it by P inverse and P. Fine? Hello? Hello, fine? Do you understand how it do? Hello?
හරි.
Okay. So then, now you know how to perform diagonalization. The another key thing is, it is properly given in some sort of problems. I will do it is in a symbolically as well. Let's say in other application is it is given in a net. Probably this will be tested in your exam, right? So let's say something given like this. Let's say you have given x dash. It is vector. It is something like a x dash. This is nothing but, let's say, x dash 1t, x dash 2t, x dash 3t. This is equivalent to, let's say, something like a11 x1t plus a12 x2t, right? x2t plus a13 x3t. Okay, so this is x21 x1t plus a22 x2t plus a23 x3t, and this is nothing but a31 x1t, a32 x3t plus x2t, a33 x3t. This is something like this. Let's say you have three linear functions, namely x1t and x2t and x3t, and you have written some differential equation which is, let's say, your first derivative of your x1t function with respect to t is equivalent to some linear combination of x1, x2, and x3. This is properly occurring in some mechanical problems, in differential equation problems. In these type of scenarios, you need to solve for x1, x2, and x3, those three functions, using these differential equations. But the problem is, if you see these equations, if you take this derivative of x1, it will consist x1, x2, and x3, all three of them. So you cannot separate these three equations and solve for one function. To assist this, we use diagonal values. Okay, so first we forget about let's say first we forget about the functional values. It means first we forget about these are functions, and then we write it as some sort of a matrix, right? Let's say we can write this as this sort of matrix. It's nothing but you take some x bar is nothing but, let's say, I denote x1 bar is vector as something like this. Oh, sorry, x bar is something like this. X bar is something like this. It's my vector x1t, x2t, and x3t. Okay, so I denote something like this, and I denote x bar my vector as x1 bar t, x2 bar t, and x3 bar t. It means I just denote this this thing as a vector like this. It is just a notation, and I take my three functions as a vector and I denote it as like this. So then I need to solve this in a very easy manner. So what we're gonna do is, I get simple substitution, something like this. I get y bar t something like this. It is y1t, y2t, and y3t. So don't worry about these functions, just treat them as numbers and matrix multiplication, numbers and vectors, right? So this is just less symbol, right? So you can just treat it as symbol. So don't worry about these functions, how it become vectors. It is nothing to worry about. Just treat it as numbers, and you can perform any of the linear operations you perform on numerical matrices and vectors. You can perform them as well. Instead of numbers, now we have some sort of functions. Just think of as, because if you notate in this way, it is easier, because if you define some a vector like it's like a11, a12, and so on. Let's say a13, a21, a22, a23, a31, a32, a33. These type of vectors, if you define AX matrix product, you can simply represent this set of equations as a matrix equation. That's the only reason we write these equations like this as representation like this. There's nothing to worry about. These are functions, how we become vectors. These are heavy calculus. Nothing more than that. You just denote it as vector to easily notate the system. Okay. So then you get y1t as this, and you get a substitution. I write this as y vector. I just denote this as y vector. The same thing. I write P inverse, right? P inverse X. P inverse is nothing but these A vectors P, right? If you find the eigenvalues and eigenvectors, you can, using eigenvalues, you can write this vector P of your vector A. If you, because you can, now we can write this to an equation set is equal to x bar dash equals A X. Okay. So using this vector, because this is a real matrix, so you can find the eigenvalues and eigenvectors. So eigenvalues and eigenvectors and eigenvalues. So you can, you know what are the eigenvalues are and what are the eigenvectors are. You can simply follow the steps I described earlier. Then you can use this substitution. What will happen is, let's say now you can have the equation AX bar is equivalent to, AX equivalent to x bar dash. So it can be proven that y bar is equal to P inverse x bar. Because in matrix multiplication, if you don't know how this comes, actually in matrix multiplication, you can treat this as a constant. You can treat this as real functions. Like, let's say you can have y equals AXT. Yt equals AXT, you can have y dash t equivalent to AX dash t when A is a real number. Or let's say if it is confusion, let's say it is used some, let's say yt is equivalent to alpha xt or something. Alpha is a real number, you can write y dash t is equal to alpha times x dash t. The same applied for matrices. If you denote a function like this, denote some sort of functions as a vector, and you get a derivative with respect to its variable, it is also become vector, because if you get the derivative with respect to d, it will become a vector. It is something like this. But if you get the derivative and if you get a substitution like this multiplied by any matrix, it is act as the derivative rules we know for the real functions, because it is just the, you can just get the derivative. It means you can, this thing is nothing but this one, right? This vector is nothing but P inverse times x1 dash t, x2 dash t, x3 dash t. It is actually, you can prove that it is actually simple derivation. So you can just memorize that, right? You have to just, if you differentiate it, you have just consider this matrix multiplication. So then what you can do is, you can make this substitution. You can have P inverse, okay? P inverse x dash, you can have x dash is actually nothing but P y dash, because if you multiply both sides by P, this P inverse will be cancelling out. So then what you can have is, actually you can have something like this. Now you can have AX equals x bar dash. So x bar dash is nothing but, instead of A, you can put, what is the solution? Instead of A, you can put P inverse dP. D is nothing but your diagonal matrix. And instead of X, you can put, let's say, wait a minute, I think I made a mistake. Okay. So let's say I put AX, now my equation set is equivalent to AX. Okay. My AX vector. So then I have the substitution that something like this. I can have the substitution. I can have P inverse y equals P inverse x. Okay. P inverse x. So then make the substitution. X bar dash is equivalent to P inverse dP. Okay. So this is my, I think I got that one. Yeah. P inverse dP. So then my x variable is equivalent to my x bar thing. Okay. So then this is nothing but, I think, yeah. So then I can have this equation. Then what we have to do is, I have to, I think, I do something wrong here, right? Yeah, I think okay. So I think I have to get the substitution here. I think I didn't mess up with the notation, right? Because it is, yeah, so sorry, this is nothing but I think I mess up with this one, right? I think yeah, I am writing in correction order. This is P1 P inverse AP, right? So this should be P inverse AP. Otherwise, it will be some sort of difficult. This should be P inverse, so this should be P, right? So sorry about my bad, right? P inverse. Okay, so here actually it is only the P inverse change, right? P and P inverse. Okay, so because it should be this is equal to D, right? So this is equal to D, so you can just multiplication. So the revised equations are this should be because I write it this correct. I just messed up it here, right? So yeah, I think I showed that one. So it here, right? So it is here. This is the correct equation. So then I can have to put this not P inverse dP. It is P dP inverse X. Okay. So then what will be happen is I can write this thing as my Y. So I can have X1 dash equals P dy. So now I can have my Y bar is nothing but, I know my Y bar is nothing but P inverse X bar. So then I can have P inverse. So not I have. So I can have now my X inverse P inverse X bar. So I can have my X bar as P Y bar. So then what I can do is I can make the substitution here. P Y bar is equivalent to P D Y vector. So then I can multiply by the inverse of this Y1 bar equals P inverse D Y vector. So it is P inverse P. So this is identity matrix. And I can have the simple equation that Y bar equals dy. Okay. So then using this equation, this is something like this. Y1 bar T, Y2 bar T, Y3 bar T. Okay. So this is something like this. You have diagonal matrix lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. And you can have Y1T, Y2T, Y3T. Something like this. In simple terms, you have the simple equation. You can write Y1T by equals lambda 1 Y1T. And you can have Y2T dash equals lambda 2 Y2T. And you can have Y3 dash T, which is equal to lambda 3 Y3T. So then you can easily compute, let's say Y1T is equivalent to, let's say, alpha 1 times e to the power lambda 1T. You can get one Y1 dash T is equivalent to lambda 1 alpha 1 e to the power lambda 1T. It is simple calculus. So this is nothing but Y1T. Okay. So solution to this type of equation is Y1T into lambda 1 dash equal to Y1T. It means your function's derivative equal to some constant time your derivative. You can easily say that it is your Y1T is equivalent to some constant alpha 1 times e to the power lambda 1T. In the meantime, you can also write your solutions, right? Y vector is nothing but Y1T, Y2T, and Y3T. You can write easily the solution as something like this. Alpha 1 e to the power lambda 1T. In the same way, alpha 2 times lambda 2T. And in the meantime, alpha 3 times e to the power lambda 3T. This is the solution for my Y vector. But now I know I get my Y vector as P inverse X. So I know my X vector is P times Y, because I have to multiply both sides by P, right? Because if I multiply both sides by P, this to this cancelling out. So then if I want to find my X1T and X2T and X3T, most of students, what they're doing the wrong thing is they stop here. This is not the complete solution. This is the solution for our substitution variable y, our substitution vector y. If I find this one, we have to put our P inverse matrix here. It is nothing but this is my E1, E2, and E3. And I can have my other vector. It is alpha 1, e to the power lambda 1t, alpha 2, e to the power lambda 2t, alpha 3, e to the power lambda 3t. So you can have, your eigenvalues. It is nothing but some linear combination of these three functions, y1, y2, and y3 functions. Your x1t is some linear combination of these three. It is determined by this eigenvalue. Your first eigenvector. And the second solution is nothing but linear combination of these three functions. It is a linear combination of your second eigenvector. It is determined by your second eigenvector. And the third function, it is again a linear combination of these three, and which is determined by the linear combination determined by the third eigenvector. Did you get the point? Hello? Hello? Fine? Hello? Fine? Okay. So these are the things you need to know about eigenvectors. So then you know how to deal with solve the solution for differential equations and get the equation. Probably this will be two questions you can have. First question, you have to find eigenvectors, and then you have to find eigenvalues, and then you have to find eigenvectors, and then you have to find diagonal matrix. It means you have to find D and P, and then you have to use this thing to solve differential equation. Okay, so okay, these are the things actually did in the eigenvalue sense. The next two things are actually on what you called singular value decomposition and also QR factorization. So I think those two topics will take some of, I think, more than 1.5 hours. So I think I just got the message that your quiz is postponed, so I can do it on another day. I will share the recording. So because if you have any problem with these things, you can probably ask now, because it is actually probably all thing about eigenvectors. If you know these two things clearly, you can easily get away with any type of eigenvalue problem, because I have covered how to find eigenvectors and how to diagonalize the matrix and how to solve the differential equations. And other than that, you have some sort of theories, like let's say what are these unitary diagonalization, how to diagonalize, orthogonally diagonalize the system, how you find the powers and so on. That's why I discussed. But sometimes you can have there's a theory called, if you want to diagonalize your system orthogonally, your matrix A should be orthogonal. Sorry, should be symmetric, right? So if you want symmetric, if your matrix is symmetric, you can diagonalize orthogonally. It means you can have something like P, let's say, I forgot about one's other thing. I think it is, my equation is, I think, I cannot mess it again. Let me check. I think it is P inverse AP, right? P inverse AP means it is PDP inverse. It is my A. I can write this thing as something like PDP transpose equals A, because if your matrix is symmetric, this vector columns become orthogonal and orthonormal at the same time, because you can normalize the vectors by their norm at any time you want, right? You can just have to divide it by the norm, but to get the orthogonality, your matrix should be symmetric. And there are several theorems to find how the system is linearly dependent and how you find non-zero matrices and so on. There are some 10 criteria. I think the note I share you, there is some section on that, so you can probably refer that. Up to this point, if you have some another problem, you can probably ask me now. Hello. Hello. Okay, so I will stop the recording now. So you can probably, if the quiz is postponed, you can probably contact me and I can contact another one. Please contact me before Saturday, right? Because I have my batch event on Saturday. It is a cricket match, so probably if your quiz is on Sunday's evening, I don't think that It's how to see, because I am not stepping the ground. I think around 2 to 3 years. So if I step on the ground in Saturday and play some cricket match, and sometimes I think I won't. Yeah, let's have to see, because sometimes most of our best mates will be on the bed on the next day. That's how it goes, right? You know how it. You go to a ground in a very after a very long time. So okay, so I think, sorry for very late notice. I think I just saw the message for your rep, I think in the morning, and I just conduct this. So I will share the recording, so you can go through the recording, and also if you have any problem, you can ask. So that's all in the eigenvalues chain. Also, I will share some sort of YouTube playlist with you. That's where I learned more about these things. Actually, it is around, I think there are I think 4 to 5 videos around 20 minutes. So there are very clearly explained from the Imperial College of London, some Coursera course. I will share you the YouTube videos of that as well. So you can share, you can watch that, because they are using how what eigenvalues are really mean, what are the vector transformation. Really good of if you go through that their linear algebra course, I think they are very clearly explain how it happened. So it is actually really good thing if you can go through before the mid exam. I think you will probably, I think that video is it's a good Kuppi itself, right? So that's a really good dash, because I learned a lot of them even after my linear algebra course. After semester 4, I learned those, but they are pretty much useful. So that's how I do these calculations. They are so how your determinants need to be equal to 0. So what did this actually mean? So then you don't have anything to memorize, and you can do anything you want. So I will stop the recording, and you can probably arrange a date and let me know. I know there are power cuts and so on. So please, it is good we can arrange a daytime, and please let me know early. I can do another one if you want. Okay.